don't need it. No, there's still a light on. Anyways, today is Earth Day, and Earth Day has been celebrated on April 22nd since the early 70s. There are a lot of science marches today. I'm glad to see some scientists not marching or marching here to the UConn campus, but sitting still for a little while. And on Earth Day, there are so many various events that are being held to demonstrate support for environmental protection. And because it is Earth Day, it's particularly apt that we have a keynote speaker who bridges the field of chemistry and the geological sciences and who focuses on the understanding the drivers of the variability of Earth's chemical systems over geological time. And on a personal note, I mean, we always say chemistry is a really broad field, and you can do so many things with chemical knowledge. But then there are these moments where you think, wow, it's really that broad. And one of those moments was when Professor Michael Wren applied for the job here, and he gave his talk. And you have the privilege as a professor to see many talks every week, every month, every year, and we keep saying, chemistry is so broad, and yet 99% of the talks fall within a very narrow regime of expertise. And then came Michael Wren. And he presented a talk that was, to me, absolutely eye-opening, and I said, wow, I've never even thought about this. I never even considered that is possible, and this is how we know the climate work at geological timescales. And this we remembered when we were looking for a speaker for this event on Earth Day and bridging geosciences in chemistry and so on. So, Professor Michael Wren, particularly happy to introduce him, one of our own assistant professor in the Department of Chemistry with appointments to the Center of Integrative Geosciences. He got his bachelor's and master's degrees in earth science at Dartmouth College, and then he went on to get his PhD at Stanford University in geological sciences, and then after postdoctoral appointments at Yale and University of Michigan, he joined UConn in 2012, and I'm happy to introduce him and have him tell us about the science.
So thank you, Christian. That was a very kind introduction, so I really appreciate that. And if I'm not loud enough, feel free to holler at me. I'll put on the mic. Generally, I try and avoid that if possible. But when Christian and Mark asked me to talk today, I thought about what I might want to talk about. As he mentioned, as a geochemist, there's a lot of different things that I do. My hands in a lot of different pots. But given the context of the day, given the context of debates over climate, debates over the role of science in our society, funding for science, I really wanted to bring something back that thinks about the contribution of chemists and physical chemists in our understanding of the Earth and its history, and how, as we look back through time, very frequently in our past, as we've evolved in the field of physical chemistry, there's been a very close connection between chemistry and neurosciences. Many of the early physical chemists were fully enmeshed in this exploration of the natural world. So I'm going to touch on this. We're going to be a little bit history story, a little bit understanding of basic principles of atmospheric chemistry, and then a little bit about what I do to try and understand how we know what we do about atmospheric CO2 over time. How do we know, or how do we predict what might happen in the future, and how does this all tie together? And this is set within this context of a background of data coming out every day about changing temperature. So you've seen this probably in the news, unless you've been hiding under a rock. People have been making measurements for hundreds of years, and there's arguments going around that, broadly speaking, temperature is changing. And we can see that whether we're looking at Arctic ice, whether we're looking at thermometer readings from around the globe. And this is also set in this context of a background rise in atmospheric CO2. And so you're looking on the right at what we call the Keeling curve, developed by Charles Keeling, who was a PhD chemist from Northwestern, who then went on to a postdoc in geochemistry at Tech and started measuring CO2 in the atmosphere. And so we see this long-term rise in atmospheric CO2. And this is also set in the context of arguments about this idea that, fundamentally we are in a glacial world. We've got glaciers on both poles. And from the perspective of the role of CO2 and other gases in monitoring, in stabilizing atmospheric temperature, above 350 parts per million, many would argue that's a fundamentally different state. It's a non-glacial state. So we have this question. We know atmospheric CO2 is changing. What does it actually mean? Right? That's the fundamental difference. What's going to happen? So it is Earth Day, right? It's also March for Science Day. And I wanted to throw out just a few key pieces of data here when we start to look at atmospheric PCO2. So on the very first Earth Day, so over 40 years ago, PCO2 was at about 325 parts per million. By the time many of the graduating seniors in this room were born, we were about 365. Today, or rather last month, we were at about 407.5 parts per million. We recently surpassed 410. So, indisputably, CO2 is changing. Right? It's increasing. So, we're left with this question. Is the current amount of CO2 in the atmosphere normal for the Earth as a system? Right? We're all here. We're all doing fine. It's not too hot yet. So, is this normal? If it changes, is that still normal? What does the world look like with high PCO2? So I've got a little bit of a video here, so just as a little plug for what many of our fellow scientists do. In the last 30, 40 years, we've had fundamental changes in the types of data we get. We've got satellites that are evolving, we're able to measure things every day. This is a nice compilation from NASA, which is a simulation of a year in the life of CO2. So this is daily emissions of CO2, and it's based on actual measurements and run through supercomputers. And so there's a few things that I want you all to observe. So the first is when we look at this, red means high CO2, the blue or the darker colors mean low CO2. You can see the date change in there, so we're in March right now. And broadly what we can see is a few key features. So the first, if we look here in, say, the Amazon region, you see this flashing. And when we look at the changing date, right, this flashing is happening every day. This is essentially the Earth breathing every day. This is the response of plants on the planet taking up CO2 as they have available light energy. Sunlight goes away, they're not taking it up. So the Earth breathes. It's a biochemical system. We're taking up CO2, releasing it every day. The other thing we can observe is we can see the broad features of the atmosphere. So we can see this kind of westerly wind direction in North America. We can see these vortices moving across the planet. We can see different directions of the tropics here. We're also seeing now variations in the color. So we're seeing changes in the amount of CO2 present in the atmosphere for any day. And so what we're observing is daily cycles and annual cycles. We're seeing changes in light energy. Plants are taking that energy, using it to fixed carbon, so they're taking up CO2, building biomass. So throughout the course of the year, we have extremely high CO2 concentrations in the northern hemisphere. In the late winter, as sunlight returns, vegetation starts to kick into high gear. We suck up that CO2, we drop it in the atmosphere. We see a shift to the southern hemisphere where it's now got more light, but not as much. There's not as much land mass down there. So we can see this Earth system breathing. Now, that's a single annual cycle. In the context of humans and the environment today, we're combusting fossil fuels. I drove my car to get here. I probably drove a little faster than I should, so I'm burning a lot more fuel. And we all know that we all drove here, we like to fly on vacation, go nice places. We're going to keep burning fossil fuels. The question is, depending on what we do, where will CO2 end up? So the IPCC, the Intergovernmental Panel on Climate Change, has put together teams of scientists around the globe to come up with different scenarios. And this is just kind of an envelope of different end member scenarios of where we're likely to end up with PCO2. If we enact radical change, maybe we'll end up somewhere between 500 and 600 parts per million in the next 100 years. If we just say, heck with it, let's just burn it all. We're going to end up somewhere considerably higher. So, what's going to happen? So what I'm going to go through now is really how we think about the evolution of earth sciences and physical chemistry, how these, kind of this intersection allows us to think about the Earth as a system through time. So this is a cartoon schematic of Earth history going from 4.5 million years to recent. And I'm going to talk about this in the context of atmospheric CO2, thinking about the feedbacks of CO2 and climate, how Earth actually records information about its climate in the geochemistry of biological materials, inorganic materials, and what this might tell us then about future change. So if we think about the last few hundred years, right, where we sit today, we have a wide array of analytical tools at our disposal. We have broad expertise in multiple different disciplines. We're starting to really go down into really small details in different aspects of chemistry. But if we step back and we think about the evolution of the field, really the term physical chemistry was first coined over 250 years ago by a Russian, and really putting together this idea that we have to have some discipline that's going to explain the physical experiments for what's happening in complex bodies through chemical operations. And modern physical chemistry really started to blossom in the 1800s, really from the 1860s to 80s, with evolution of kind of major advances, right? So the thermodynamics, electrolytes and solutions, chemical kinetics. And we know many of the names from that era, Ostwald and Hoff, Arrhenius, kind of key players who, many of whom got Nobel Prizes in the early part of the 20th century. Now, if we think about this as this branch of chemistry concerned with applications and techniques about these chemical systems, you look at who was developing the field and what they did, what their training was. This was a time of evolution of our whole understanding of the Earth as a system. Right? So we were having fundamental advances in not just chemistry, but physics, geology, biology. This was this nexus of major advances in many disciplines. And the early scientists of the industrial age all seemed to wear many hats. They were well versed in what was going on in not just their field, but other fields as well. And I think one of the key things of this time is that major advances in these fields were linked to technological innovations. So if we think about kind of the major players in understanding of the atmospheric system, there's a few key people who I'm going to talk about and how it connects to what we do. And one of the first, really for what I do, is thinking about John Tyndall, who is an Irish chemist, physicist, geoscientist, who was really one of the first players to get into the idea of how significant it is to have water vapor in the atmosphere, or to have CO2 in the atmosphere. He had these questions, right? There have been ideas bouncing around that different gases might have different absorptive properties, right? They may absorb different wavelengths of energy, retaining heat. And he argued that atmospheric water vapor, or CO2, are likely to play a significant role in changing the heat budget of the planet. He didn't have tools to measure it, so he invented his own apparatuses to actually put gas into the tube, right? Measure the pressure, heat it on both ends, and look at essentially the absorption of energy. And what he came forward with was this idea that water vapor is a fundamentally important gas in constraining the Earth's climate. That without water vapor, we would be a cold planet. Likewise, he argued, CO2 is a trace gas, but it plays a fundamental role in keeping our planet warm. Now, I would also make the argument that these advances in physical chemistry did not arise in a vacuum, right? These advances were happening at the time with other advances in disciplines like geology and biology. And so, likewise, around the time you have people like Louis Agassiz, who's a Swiss geologist, who's observing the natural world and making these arguments that it looks like if we step back to the past, we've had variations in global climate. We've had advancing ice sheets through time. And likely we've had these ice sheets flowing not just from the Alps, but southward onto the plains of Europe, North America. And we look at that, now we know that we had massive ice sheets on the scale of North America. So you have this nexus of knowledge building. So then by the late 1800s, you have someone like Svante Arrhenius, who many of you probably heard or used his equation before, really thinking about the Earth system in the context of changing climate, in terms of changing atmosphere. So in 1896, putting together a manuscript on the influence of carbonic acid in the air upon the temperature of the ground. So he was intimately familiar with what the geoscientists were saying, but yet he was able to use his knowledge as a physical chemist to think about how these two play a role. And he came up with a few important predictions that really stick with us today. The first is that the atmospheric envelope is limiting heat loss from the planets. So we've known that, at this point for about 100 years, but these ideas were further developed by people like Tyndall. And they came up with this idea of this hothouse scenario. So thinking about the Earth as a greenhouse, like we do today. So in 1896, they have the theory of global warming, of thinking of the Earth as a greenhouse. And he also argued that the ocean is one of the major sinks for atmospheric CO2. So we can suck it up into the ocean, and so if we burn fossil fuels, the oceans are going to suck that up. Now at the same time, right, so people are starting to understand we've had glacial ages, we've had advances of ice sheets, retreats of ice sheets. They were worried, are we heading back into an ice age? So there was a fear, should we worry about major ice sheets, covering London? And he argued then that we know that we've had alternation of glacial periods and warmer periods. So should we all worry about running to Africa to a warmer climate to escape this, this rapidly advancing ice sheet? And he said, right, the enormous combustion of coal by our industrial establishments suffices to increase the percentage of carbon dioxide in the air to a perceptible degree. So at this time, 1896, he knew burning fossil fuels is going to change the atmosphere and it's likely going to stave off an impending ice age based on basic principles of physical chemistry. And he provides us with even more information, a specific prediction. So he argues that if the quantity of carbonic acid increases geometrically, then the temperature is going to increase kinetically. And specifically, that you could do simple calculations in 1896, remember to look out there, that if you increase carbonic acid 2.5 to 3 times the present value, so at that point about 280 parts per million, the Arctic would warm 8 to 9 degrees. So that's a prediction. So what that tells us then is that can we look at Earth's past as a means of understanding the future, right? Did that prediction bear out? So ultimately what we can do then is we can think of the Earth as a chemical system. So if we step back, you're all familiar with experiments in the lab bench. Right? We've all worked in our hoods, with our beakers. We have a chemical system. The Earth is just another chemical system, but it's a lot bigger. Right? There's a few more components, but it's just a big beaker. And we can think about this, here we are today, something or CO2, but it's a chemical system, 8,000 kilometers in diameter. And we know that over long time scales, so if we're thinking about our lab bench experiment, time is just extended a little bit. Earth's chemistry dictates the ocean's atmospheric life. But on the human time scale, what we're really doing is we're perturbing just a part of this reactor, this thin veneer, maybe tens, maybe hundreds of meters thick, this critical zone essentially. So how do we actually test a chemical system? Well, we can perturb it. So in the case of the Earth system, we can turn up the dial, we can change CO2, we can change O2, we can change water vapor. And to do that, we can look back to the past. All right, so we have this question. What do we know about the state conditions for the past? How do you know it, and why should we ever believe it? Because one thing I always teach my students in class is question authority. Don't just believe me every day, question it every time. All right, so if we look at, and I'm going to jump ahead just a tiny bit here. This is just a sped up version of looking at atmospheric CO2 over different time scales. And what you're looking at is actual data from the late 80s on moving forward. So what you can see is all these points here represent actual sites where we're measuring CO2 in real time. So these are going into the 80s. They're set up by a variety of different institutions around the globe. And what we can see is here's our latitudinal profile here. So these are all our sites, and what we're seeing is this up and down is the annual breathing of the Earth. What we can see though is the northern hemisphere is moving up and down much larger amplitude. So essentially this is the tail that's wagging the dog. The northern hemisphere controls everything. But what we can see is over time we're steadily progressing upward. And we're moving. This is called the pump handle of the Earth. So every year, a little bit more, we're moving up. And we can see this fundamental change of baseline. And so we can see as different countries kind of advance in their own scientific funding, they bring on board new monitoring stations and so forth. So we're moving up in time. So the question is then, all right, this is the interval with which we can actually measure. We've got satellites, we've got physical measurements at multiple sites. How do we then scale it back? If we think about where we're heading, how do we put it in the context of Earth's history? Because as we're approaching here now, this is going to stop at 2016, how do we step it back through time? So these are now taking the original measurements of Charles Keeling, who was physical chemist, Scripps, and measuring these at Mauna Loa. So we're moving back to these first measurements in the 50s here. But we're going to step back further now. So atmospheric CO2 in the context of longer time. Right, so as we move back further, here we are today, going back 1,000 years now. We're going to step back a little further in time. So pre-industrial average about 278. Today we're actually now higher because I can't change this fast enough. We're going back thousands of years. So again, think about 20,000 years ago here in Connecticut, we have kilometer by a city right on top of us. So look up a whole lot of ice. As we move back through time, CO2 essentially bouncing between 180 and 280 parts per million for the last 100,000, 200,000, we're going to keep going all the way up to 800,000 years. So how do we actually know this? Where does this information come from? Certainly this is distinct. Now if we think about the way we measure this, well, in recent time periods we've got the physical measurements. From the 70s on, we've got satellite data. If we go back further, we've got written records. But if we want to go back deeper in time, we need physical data sets that are recording information at the time of form. So what we need are geochemical records, fossils, and other data sets. On the time scale of 1 million years, we can go to Greenland or Antarctica. We can drill a kilometer to 3 kilometer hole, collect that ice. So here's an example of what this looks like. You can see individual years in there. And we can pull out dissolved gases within these ice and look at variations between temperature and see methane or CO2 and see this close covariance of it. If we want to go back further though, we need something else. We need geochemical properties. Right? Something that the Earth is either biologic or inorganic systems are producing that get preserved through times that we can then go and measure. So what I and my students do is to fundamentally focus on one signature, which are stable isotopes. And so you probably heard about these in one variety of class or another. But we're talking about isotope species. So atoms of the same element, different number of neutrons, same number of protons. So they're not undergoing radioactive decay. And the common ones you might be familiar with are oxygen, 16, 17, 18, and hydrogen and deuterium. And the distribution of isotope species, if we think about why we have them, this goes all the way back to nuclear synthesis. Right? We're forming these things early on after the Big Bang, or we're forming different isotope species as a result of nuclear synthesis within stars. And if we look at the Earth, or solar systems like Earth, we see characteristic distributions of these isotope species. We're familiar with O16, so over 99.5% hydrogen deuterium. Almost 99.98% is hydrogen, tiny bit deuterium. But we can measure this. And we can look at the ratio of the heavy to light isotope in some sample compared to a standard. And we can record that for different parts of the system. Now let's go back then again to another physical chemist who discovered deuterium. So Harold Urey, also another Nobel Prize winner. So it makes me realize I need to discover something. I'll get that Nobel Prize. So he was really intimately involved in thinking about, all right, what do we know about the distribution element? He found deuterium, but at the same time, he was kind of an amateur geoscientist. He was really interested in the evolution of the Earth, the understanding of changing temperature, thinking about how life evolved on Earth. So he published a very important paper, Planetary Origin and Development, and then jumped into this idea of thinking about how life might evolve in the early atmosphere. But this key piece that he did here was thinking about isotope proxies, or isotope measurements, as a recorder of temperature. And this comes down to the idea that in any molecule, we have atoms that are bonded to another, that we've got differences in bond energy as a function of their mass. So if we think about any molecule vibrating in space, different masses of those key elements result in different vibrational energies. And if we think about all the processes that we do in the lab, where we're making and breaking bonds, anytime you're making and breaking bonds, you have the possibility of fractionating based on energy differences. And so we can think about fractionation in equilibrium systems, kinetic fractionations. There's a mechanism for imparting differences in So we have a mechanism for fractionating these systems, for partitioning between different components. And so what Urey was able to posit then is that, well, if we think about something like this, a shell, so made of calcium carbonate, it's incorporating oxygen from the water. We can exchange a heavy or a light isotope into that physical component. And as a function of temperature, we're going to have differences in the magnitude of fractionation, or partitioning between the two components. And if we were looking at a system where we might have oxygen, we might have one setup, so we might have 1 degree of variability. If we're looking at a system with hydrogen, it's a different magnitude of change. But the key point is that temperature plays a key role in fractionation of magnitude. So we can bring this back to the laboratory. And this is an example of what we use in my lab. Analyze this on a linear-type mass spectrometer, where we can turn a sample into gas. We can ionize it, send it through a magnet, and separate it out by mass, and measure the ratio of these different masses in Faraday criteria. We can actually measure minute differences in the isotope composition. And just as an example here, if we were looking at hydrogen deuterium ratios, we can clearly distinguish between ratios of this 0.00150, right, and this. That's really small. And we can measure that in a whole host of different systems. Now, just to show you that this is actually true, if we look at oxygen in precipitation around the globe, what you can see is very large differences, and broadly this is related to temperature. So we have a process that is imparting a signature. We can measure that. And if it's recorded in things over a long time, we can reconstruct that record. So if you want to go back then and think about 45 million years or 65 million years of history, we can take something that is produced by a chemical process, in this case, shell, right? And virtually everything here, right, is produced by a chemical process. I can sample my hair, or my fingernails, or my teeth, and tell you about what I ate, right? So materials are produced by a chemical process, die, sink to the bottom of the ocean. We can analyze the isotopic composition and reconstruct temperature. Unfortunately, the U.S. government and other governments, because of fears of Russian subs, and I guess back to Korean subs today, they want to know what's going on the bottom of the ocean. We've gone all over the world and drilled the bottom of the ocean. Bring those cores back, and scientists get to play with them, but really under the guise of science, but really we're just trying to understand the bottom of the ocean so we can hide subs or find hidden subs. So we can sample these cores and go back through time and reconstruct temperature curves for the last 65 million years. CO2 and temperature are linked over a long time. So we know that if you were to hike around in, say, Wyoming or Montana or the high Arctic, which I'm going to eat my polar bears up there, there were periods of time where the Arctic was 10 to 12 degrees C median temperature. So as an example, Connecticut today, median temperature is somewhere around 13 to 14 degrees C. So the Arctic is some kind of hippo creature up there, hanging out there, 10 to 12 degrees C, 20 degrees C in Wyoming, so that's equivalent to states of Savannah, Georgia. All right, so now touching on kind of what we do in my lab, how does the Earth system respond to these perturbations of CO2? What do we actually see in terms of data? Can we quantify it? I'm going to show two short examples. So one is this late Paleozoic period, 300 million years ago, where we look at glacial and interglacial variability, and then briefly this transition from what we call this hothouse world, so 35 million years ago where TCO2 was over 1,000, to this icehouse world where it's maybe half that. So what happens in these scenarios? So quick snapshot, 300 million years ago, so it's fun to think about this idea that the world is changing, right? Nothing is static. Here we are in Connecticut, somewhere down here. So everything's rotating. We're on the equator now. Big mountain range. We see these all the way up central Massachusetts, New Hampshire today, the remnants. So here we are on the north side of these mountains in the tropics. And just to frighten everyone, these are the types of critters that were running around. I would not want to be up in the south. Right? The reason these things were so large is that they don't have a vascular system. They can't pump oxygen to their blood. They're diffusion limited. So we have a period of high CO2 at this time. Or high O2 rather. All right, so this late Paleozoic, this is the last fundamental period in Earth's history that is similar to today with varying CO2 layers. What we have is these bizarre forests. So here's a photo from one of my colleagues of these intact trees in Illinois. So going up 30 meters in some of these things here to see. Now what's unique about this then, right, they look pretty, but what can they tell us? Well, if you think about the way that biology functions, right, so again, it's just a series of chemical systems. So on the surface of these HLEs, we have preservation of the original structures, right, of these kind of biosynthetic structures. And we have particular wax, we have, in some cases, cellulose fibers, probably not sold. But if we relate this to modern, we have very large differences in the types of compounds that are produced by different plants. What's important, though, is vegetation produces this. We can see from the photo here, they're also preserved. So anytime you're producing a compound by a series of chemical reactions, unless you are fully exchanging that or breaking that compound, you're preserving a record of that biosynthetic process. So we're preserving the chemistry of the process. So what we can do then is we can relate that to CO2. We can actually work with plant physicists who study plants and think about them as a series of pipes. So it's essentially a fluid dynamics problem. We can work with people thinking about how they function, how they're diffusion limited, how they incorporate CO2. And we can relate this to CO2 records. So we can see at this time variations in atmospheric CO2 300 million years ago. In my lab, we can then take these leaves, we can pull them out, we can extract out these biomarkers from the surface of these leaves. In this case, we'll look at normal alkanes because they're preserved well. Right? These provide a variety of uses. We reach out ahead, we can look at individual leaves, and ultimately, we can march through time, in this case, hiking up a mountain. Right? So this might be 3 or 20 million years on that mountain. And we can pull up the biomolecules and relate these to environmental parameters. So what we see then is if we look at carbon variability, in the back here is atmospheric CO2. In the front is what's recorded by these plants. So we see this up and down variability through this glacial interglacial period. When we look at hydrogen, again, following our changes in CO2. And when we compare that to modern, right, so recent glacial interglacial period, we can see data showing similar processes for equatorial regions. So who cares? Well, the magnitude is very similar. So what this tells us then is that over long time scales, we think about the Earth as a chemical system. that we've had this vegetation atmosphere feedback similar to modern for hundreds of millions of years, meaning the system functions today similarly to it did how it did 30 million years ago. So as a process, right, we can look at variations and say, yes, this is a good analog for what might happen in the future. It tells us that climate sensitivity is this intrinsic property here, and that we can see similar variations in sensitivity. Now, if we jump forward to recent transitions, so going from this world with crocodiles in Wyoming to something more similar to today, 34 million years ago. So here we are, more similar to what we see, but unfortunately in Florida, because all the ice is gone. And you can see here, Europe and Africa have not collided. Now this is a period where we're essentially moving from high CO2, 1,000 parts per million, down to 500, 560. So this is the period going from no ice on Antarctica to ice, with a drop in CO2. So when you think of this as going from something like this to something like this. So I'm going to show you quick data from two different sites that we work at. So first, if we go to North America, beautiful places to go see. This is kind of my excuse for getting outside. We can go and we can sample these beautiful badlands terrain, going through this time interval, so we have deposition through this period of change. And what we can do is we can analyze the chemistry of these sediments, look at these hydrogen isotope variations or distribution of these molecules, and we can see fundamental shifts. This is moving through time, getting run report at the top. Basically, big shifts in these intervals. So what that tells us then is that in this case, time is here, that we have periods of changing CO2, changing global temperature, changing moisture availability, and changing local temperature related to this fundamental drop in CO2. So CO2 is tied to local changes. If we go to similar sites in South America, right, we can go to other places in the globe. And the real reason we go to South America is not because it's amazing, but because they have amazing wine mountains. Any excuse to bring that here we can. But we can look at data, we can extract these biomarkers, bring them back to the lab, analyze the hydrogen and carbon chemistry of these, look at these variations, and again, we see temperature change on the order of 4 to 5 degrees. And when we pull these in a larger data set, right, looking at multiple sites, we see globally dropping CO2, having CO2, temperature shift somewhere around 5 to 8 degrees during this interval. So what we see then is, going back deep in time, 300 million years ago, this coupling between CO2 and glacial advances. We go to younger time interval, hothouse to icehouse rather, a drop in CO2 is linked to this fundamental temperature shift. So there are these strong connections between CO2, temperature, and ice buildup. So if we bring this back together then, thinking about projections for a future world. So here we are today, somewhere around here. This is world CO2 emissions in terms of gigatons. So one thing that I think is very important for people to recognize is if you look at development industry today, development of power generation, almost every week in China there's a new power plant. And that's coal that's being built. The average lifetime of a power plant is on the order of 30 years. So whatever we're building today, we can anticipate will be here for another 30 years. So 1 a week, 30 years, and that's just one country. So we can anticipate some variable increase in CO2 emissions over the next 50 to 100 years. What we don't know is where we'll end up in terms of the equilibrium stabilization of CO2 concentration in the atmosphere. Keep in mind that barring human intervention to remove CO2 from the atmosphere, which is really implausible, it takes on the order of 2,000 to 3,000 years for the Earth to re-equilibrate to drop CO2 back down. Right? So between biological and inorganic processes to drop CO2 down. So whatever we put out into the atmosphere is going to be here for a few thousand years. So our stabilization CO2 is going to be somewhere on the order of, at a minimum 450 up to 1,000. We don't really know. And this has implications for a range of temperatures, somewhere between 2.5 to 8 degrees. Now, in the context of Earth history again, so I think the unique piece as a geochemist that I bring is this context of time. My lab bench time scale is a few hundred million years longer than yours. Right? Same processes, but I'm a little bit more patient with this. So when we look at where we're going to head, and we think about the context of Earth history, the sun's intensity has changed over time. CO2 concentrations have changed over time. Where we are going to end up in the future is unknown, but what we do know is it's going to be higher CO2 than it is today. If we're in the low end of the scenario, we can go back to say the East 50 million years ago. That's the type of world we will end up. If we enact the strategy, which I call just burn it all, then we're going to be in something fundamentally different. We will be going back, when we think about change in solar intensity and atmospheric porosity, to a period that we've not experienced in the last 420 million years. 420 million years ago is when land plants really first started colonizing Earth. So, it's kind of a bit doom and gloom, but I think this is the reality, is that if this is the strategy we impose, the Earth system will tell us we haven't experienced that. So, how does this all impact, right? So if we think about climate sensitivity, how sensitive the Earth is to doubling the CO2, there's a range of predictions for how sensitive the Earth's climate is. What we see is a right-skewed distribution, which means if we increase CO2, the probability of a very small increase in temperature is incredibly small. Most likely, we're going to go up 2 to 3 degrees for doubling the CO2, but there's a possibility maybe it'll be 8. It's not going to be 1, but it might be 8. So think about 8 degrees, that's moving New York down to Savannah. So that's a big difference. Now, we come back though, so there's a lot of debate over the science, over how important this is. If we think about the work of Arrhenius over 120 years ago, what was his prediction? Right? A simple calculation shows that Arctic would rise 8 to 9 degrees if carbonic acid increases 2.5 to 3 times every value. At that time, it was 280 parts per million. And I would argue that people were pretty far back then, right? You know, YouTube. Spent a lot of time thinking about this. That he was right. And we can see this bear out in some of the climate scenarios today. Looking at an increase in scenario A2 here going to 800 parts per million. What do we see for the Arctic? Roughly 7, 8, 9 degree temperature increase. So we're not that far away from the predictions made by physical chemists from laboratory experiments 120 years ago. So the Earth is a simple chemical system when we step back and we look at it. There's a whole lot of complexity in biology and other pieces, but at the very core, it's a simple system. So what it may mean, maybe we're heading back to the easy, I don't really know. But what I think it really does point out, though, is that I think it's critical then for you as chemists to sit here in this room, to step back and think about your science in the context of other humanity. Many of the major advances that we've seen, certainly in this field, have been from these cross-disciplinary approaches. Thinking about what you do, how you do it, and then working with someone else. And I think that's the real strength of the data that we see here is crossing over in these disciplines. And with that, I would just like to thank certainly the chemistry department and the time for and Christian's wonderful introduction, the geosciences program here, and some of the members of my lab team, obviously not shown here as well, but, and then certainly ACS for hosting such a wonderful event today. So with that, thank you.
Thank you so much. I think we have time for a brief question before we break.
The clearing of the Amazon rainforest is a lot of press for good reason. And I'm thinking historically there are 2 other things that occur to me that were similar. One is the clearing of the European forest in about the year 1000. And then the clearing of the eastern forest in North America from 1600 to 1800. So there was actually wood shortage back then.
Oh yeah, yeah. And actually, here if you drive around Connecticut, right, you know, everyone here in New England has probably seen all the stone walls everywhere, right? So the entire region was clear cut. In many cases here for charcoal for the iron industry, putting a lot of the Canadian Revolution. So the question is, ultimately, are these types of things important Certainly in the context of shorter time scale events, yes, if we were to look at methane records for the last 1,000 years, you actually see a fundamental change in atmospheric methane due to Spanish invasion of Central and South America, right? So essentially, you have influx of peoples and diseases, population crashes, methane fundamentally changes. So these things are important, but when you step back and look at the Earth as a system, most of the primary productivity of the planet is CO2 uptake is in the ocean. So when you know phytoplankton, land is important, the oceans are perhaps more important.
I have another question. So first of all, very, very nice talk and a very good presentation, and I especially like those time snapshots, you know. So the only question I have is in regards to the CO2 concentration. I mean, I saw like, you know, like as we move to current times, the number of spots that measure CO2 worldwide increased. And is there anything like modeled into or like thought about? Because I noticed there was a whole ton of spots, of course, like where the US is. So I mean, is there any like reason to believe that maybe that has an effect that this one would have like a more balanced distribution of the measuring points worldwide? The data would look a little different,
you know,
little to no chance for
right,
that.
subtle differences. So if you think about the atmosphere as a system, right, it's a pretty well-mixed system.
Yeah.
It's a turbulent system, and so there's certainly variations. And so a good example would be if you look at, say, the Pinatubo eruption in 1991, right? So that would be our model for mixing time scales. You know, you can see particles from that in the atmosphere for a period of about 2 years, and that popped up into the stratosphere. So, you know, things are mixed relatively quickly. I imagine if we had later ratings in the southern hemisphere, we might get some differences. But broadly speaking, the atmosphere is mixed. Maybe it's half a ppm. You know, the biggest uncertainty though is that, you know, and I didn't have a whole lot of time to talk about this. Is I'm stepping back through time, 400 million years. How do you get PCO2 400 million years ago? Right? That should be everyone's question to say, I don't believe this number. No one was measuring PCO2 400 million years ago. That's a whole other ballgame how we do that, and there's greater errors in all those. But that's for things like boron isotopes, which are, you know, pH sensitive, or looking at essentially diffusion limits in different.
So you basically take the approach of model and then you refine.
Exactly. So further back in time, the bigger your errors are for things like PCO2. So these are the limitations we go with.
All right.
Thank you so much. Let's move 400 million years forward, and we will have a break now. And there's coffee, there's refreshment out there. Follow the signs in the washrooms. And then more cost that we will be putting in the prize. Have a look at next room.